Record on the computer, yes. So today we are going to discuss again the eigenvectors and eigenvalues. In the previous lecture, we started discussing eigenvectors and eigenvalues. If you have any question regarding the previous lecture, you can ask me any question. You just raise your hand and I'll unmute you and you can ask your question. So last time we discussed what are the eigenvalues and eigenvectors. I hope you know what are the eigenvalues and how to find the corresponding eigenvectors. So yesterday we stopped at the slide number, yes, here at slide number 16. Today we are going to discuss algebraic multiplicity and geometric multiplicity of an eigenvalue and eigenvectors. So according to the definition of the algebraic multiplicity, basically, if we have a matrix of order n cross n, then yes, anybody, can you repeat the last slide? So let's start with the last slide. If you say this one, the theorem we discussed last time. This theorem contains equivalent statements. If lambda is an eigenvalue of A, then lambda must be the solution of the characteristic equation which we discussed last time. It's a determinant of lambda I minus A is equal to 0. And the second is the system of equations lambda I minus A times x is equal to 0 has non-trivial solutions and non-zero vector x such that this equation must be satisfied with ax is equal to lambda x. Now the second theorem is which you want me to repeat is a square matrix A is invertible if and only if lambda is not an eigenvalue. Lambda is equal to 0 is not an eigenvalue. Why is it so? Because in the previous example we saw last time that if this A is a matrix, which is a lower triangular matrix, if any one of the diagonal entry is 0, then what would be the determinant of this lower triangular matrix? As we know that the determinant of any lower triangular matrix is the product of its diagonal entries. Then what would be the determinant of this matrix? If any one of the entry in the diagonal is 0, then its determinant is 0, because the determinant of a diagonal or triangular matrix is the product of its main diagonal entries. So if its determinant becomes 0, then A must be non-invertible. I hope you got my point. So Kashaf, Batul, you can't hear me now. You turn on your audio. I think you would be able to listen me. I hope you can listen me now. Okay. I hope you understand the second theorem. The second theorem tells us that if lambda is equal to 0 is an eigenvalue of A, then A is non-invertible. Why A is non-invertible? Because one of the diagonal entries in main diagonal, if it is 0 in the diagonal matrix in example 3, then its determinant must be 0, because its determinant is the product of its diagonal entries. If the determinant of A is 0, then A is non-invertible. So I hope that answered the question. Now we are going to discuss the algebraic multiplicity. Now let A, by definition, let A be an n cross n matrix with an eigenvalue, say lambda. Then the algebraic multiplicity of lambda is the number of times lambda is repeated as a root of the characteristic polynomial. So if there is a repeated root in the solution of the characteristic equation, then we say that the lambda has a multiplicity greater than 1. Because if the roots in the algebraic equations are distinct, then its algebraic multiplicity will be 1. For example, in the next, in this example, example 3, lambda is equal to 1 by 2, lambda is equal to 2 by 3, and lambda is equal to minus 1 by 4. No root has been repeated, so algebraic multiplicity of every lambda is 1. If we would have lambda repeated, for example, lambda is 1 by 2, 2 by 3, and the third root is again 2 by 3, then the algebraic multiplicity of lambda is 2. Similarly, algebraic multiplicity could be 3, because if lambda is 1, 1, 1 here in the diagonal, or the eigenvalues are same, all the 3 eigenvalues are same, then algebraic multiplicity of this lambda is 3. So this is how we compute the algebraic multiplicities of the lambda. I hope you understand. Now, example is here. Yes, Heather Iqbal, you raise your hand, you ask your question.
Sir, what does algebraic multiplicity tell us?
It tells us that how many times lambda is repeated as a root in the characteristic polynomial.
So
For
how is that?
example, in this example, example 4, you see a matrix A, and whenever we write its characteristic equation, we get lambda cube minus 5 lambda squared plus 8 lambda minus 4 is equal to 0. If we solve this algebraic equation, sorry, cubic polynomial equation, we can factor this equation into lambda minus 1 times lambda minus 2 whole square. Now here you can see that lambda minus 2 factor A is coming 2 times. So it means lambda, the first root of this characteristic equation is lambda 1 is equal to 1, and lambda 2 is equal to 2. And the third root is again lambda 3 is 2, because lambda minus 2, this factor is repeating here 2 times. So lambda is equal to 2 is, it has algebraic multiplicity of 2, because it is repeating 2 times in this equation. I hope that answered the question. But lambda is equal to 1 has algebraic multiplicity 1, because it is non-repeating. I hope you understand. Now we are going to discuss the second definition, which is geometric multiplicity of lambda. Let A is an n cross n matrix with an eigenvalue, say lambda. The geometric multiplicity of lambda is the dimension of eigenspace, means number of eigenvectors corresponding to lambda. Now it is possible that we get 2 eigenvectors corresponding to 1 lambda for any particular matrix. For example, in the example 4, you can see that the lambda is equal to 2 has algebraic multiplicity of 2, and only we have only 2 distinct roots. And on the next slide, and here and here, this one. Now, if we find the eigenvectors corresponding to lambda is equal to lambda 2 is equal to 2, we can see that here we get the 2 vectors corresponding to lambda is equal to 2. So what is the geometric multiplicity of lambda 2 is equal to 2? It has geometric multiplicity equal to 2, because corresponding to lambda 2 is equal to 2, we get 2 eigenvectors. So it has geometric multiplicity of 2. If on this slide we have lambda is equal to 1, lambda is equal to 1, corresponding to lambda is equal to 1, we get corresponding to lambda is equal to, let me annotate something. So corresponding to lambda is equal to 1, we get only 1 eigenvector. So the geometric multiplicity of this lambda is 1, because we get 1 eigenvector corresponding to lambda is equal to 1. So this is what the geometric multiplicity of any eigenvalue. I hope you understand. Heather Iqbal just sorry, raise the hand. You go ahead. You ask your question.
Sir, will algebraic and geometric multiplicity be always the same?
No, it is not necessary. For example, if lambda is not repeating, its algebraic multiplicity is 1. But it is possible that we can get two eigenvectors corresponding to one value of a lambda. Then algebraic multiplicity of lambda is 1 and the geometric multiplicity of lambda is 2. So I hope that answers the question. Some other person has raised the hand. Go ahead, you ask your question.
Sir, can you please repeat what is the difference between algebraic and geometric multiplicity?
Algebraic multiplicity is the number of times lambda is appearing as a root. I told you. You got it? Lambda is repeating how many times in this characteristic equation? The first lambda, which is lambda is equal to 1, it is distinct. It is not repeating. It appears only one time. So its algebraic multiplicity is 1. I have written here at the bottom, algebraic multiplicity of lambda 1 is 1, whereas lambda 2 is equal to 2, which is repeating 2 times, because we have 2 lambda minus 2, this factor is appearing 2 times in this equation, because we have lambda minus 2 multiplied by lambda minus 2, because it has square here. So this factor is repeating 2 times. What does it mean? Lambda 2 is equal to 2 is appearing 2 times in this equation. So algebraic multiplicity of lambda 2 is what? 2, because it is appearing 2 times in the characteristic equation, or it is root of that characteristic equation. And it is repeating. I hope that answers the question. So if you have any further question, you can ask me. Now, the geometric multiplicity of lambda 1, it depends how many vectors corresponding to lambda 1 we can find. If we can find, we'll discuss it with the help of an example 4, then you will understand more, I think. Then you can ask me any question if you still have any confusion about algebraic and geometric multiplicities. Okay, I hope. Now let's discuss the example. Example is what? Now we are discussing example 4 on slide 17. If we are given this example A is what? 0 0 minus 2 1 2 1 and 1 0 3. What we are going to find, we are going to discuss the basis of the eigenspace of a matrix. In the previous lecture, I told you briefly what are the eigenspaces. Now we are going to discuss in more detail what are the eigenspaces and how we find their basis. So if this A is given, first of all, we need to find its eigenvalues. We write the characteristic equation, which is determinant of lambda I minus A is equal to 0. And we solve that equation, we get this thing, which is the cubic polynomial equation. We solve this, we get the two roots, lambda 1 and lambda 2. Now, if this is cubic equation, then it must have 3 roots. We have written 2 roots, lambda 1 is equal to 1 and lambda 2 is equal to 2. There are 3 roots of this equation because it is a cubic equation. But lambda 2 is repeating here 2 times because we have 3 roots. Lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is again equal to 2. This 2 root is repeating 2 times. We have in fact 3 roots because cubic equation must have 3 roots. Now, if we get 2 distinct roots here, now what we do, we find the corresponding eigenvectors to each eigenvalue. First, we consider lambda 1 is equal to 1, and we try to find its eigenvector. How do we find eigenvectors? I told you in the previous lecture. We solve this equation. We solve, let me erase it. Well, I have to erase this thing after actually every slide. Now, we have, in order to find the corresponding eigenvector for the lambda 1 is equal to 1, we write this equation. We write this equation, and we assume that x is the corresponding eigenvector to lambda 1 is equal to 1. We put the value of x, we put the value of a, and we put the value of lambda 1 is equal to 1 here, and in this equation, and we get this one. This is the homogeneous linear system. After inserting the lambda is equal to 1, we get what we get. We get this homogeneous linear system. This one. Yes. Now, we solve this homogeneous linear system and we obtain these equations. How do we solve any homogeneous linear system? I hope you know, by using Gaussian elimination method. First we write its augmented matrix, and we try to reduce this whole system into echelon form, and then we write such kind of systems which involve a free variable s. Now we write x in this form: x1, x2, x3, where x1 is minus 2s, x2 is s, and x3 is again s. Now we take s as a common outside and we get this vector. Now this is the corresponding eigenvector for the lambda is equal to 1. Lambda 1 is equal to 1. There is a typo mistake here. Now this is the eigenvector corresponding to lambda 1. But if you see here, x is this vector times s, where s is a free variable. Now, where s belongs to R as well. Now, when we vary the values of s, how many vectors, how many eigenvectors do we get here? Infinite many, because s belongs to R and R has infinite or uncountable points. So all these eigenvectors, they make a space which will be a vector space, and we call it eigenspace. And what vector is generating this eigenspace? What vector? This vector is generating that space, which we call an eigenspace. That eigenspace, you can call it E lambda 1, which is the eigenspace corresponding to lambda 1 is equal to 1. So I repeat it. When you get the vector x, if we change the value of s, we get infinite many vectors, and those vectors, it will be a line. Yes, you are right. It will be a straight line, but straight lines are also, they form spaces. For example, in 2-dimension equation of a line, or the line, it contains how many points? Infinite many points. Any straight line passing through the origin, it forms a vector space, the points on the line. We discussed this when we discussed vector spaces. Okay, I hope you got it. So it is a line in 3-dimension R3. It must be passing through origin, because when s is 0, we'll get 0. Everything will be 0. So this straight line is passing through origin, and it forms a space. Geometrically, it will be a straight line in R3. But if we count the points on the line, they are infinite many, and they forms a space which we call an eigenspace. And this will be a vector space. And also, this space will be a subspace of R3. I hope you know what is a subspace. So this eigenspace will be subspace of R3, and this space will be generated by only this vector. So what is this vector now? We know that any set which generates a space, that set is called the basis for that space. Yes, Iqbal Heather, you go ahead, ask your question.
Sir, how is a vector space different than an eigenspace?
देखें, we have a vector space R cube. अब R cube की कितनी subspaces होंगी? How many subspaces we can find for R cube? You tell me, Heather.
Sir, बहुत ज़्यादा होंगी.
Infinite many होंगी.
Yes,
This
sir.
eigenspace is a one of subspaces of R cube.
Sorry, sir.
You got my point?
Yes, sir.
It is one of the subspaces of R cube. It is basically a straight line which is passing through origin. Now, what vector is generating this subspace? This vector.
Sir, ये हमारे पास.
So this
Yes,
vector will be the basis of that eigenspace E lambda 1. I hope you got my point. If anybody else you have any question, you just raise your hand and you can ask your question. I hope you got my point. Now, what is, yes, who is asking the question? You just raised, ask your question, start.
सर ये ओरिजिन से कौन सा लाइन पास करेगा, जो बेसिस है या पूरा जो प्लेन होगा वो ओरिजिन से पास होगा, या जो जनरेट कर रहा है वो सिर्फ पास होगा?
नहीं, ये स्ट्रेट लाइन बनेगी ना, बिकॉज एक वेक्टर है. जब आप s को वेरी करोगे तो एक स्ट्रेट लाइन बनेगी R क्यूब के अंदर, और वो अगर s 0 है तो ये तीनों एंट्रीज क्या हो जाएंगी? s को अंदर मल्टीप्लाई कर दें यहाँ पे. अगर s 0 है तो ये तीनों एंट्रीज क्या होंगी? 0 होंगी. तो मींस x इक्वल टू 0 0 0. तो 0 0 0 पॉइंट जो होगा वो उस स्ट्रेट लाइन के ऊपर होगा. व्हाट डज इट मीन? कि वो स्ट्रेट लाइन ओरिजिन से पास करेगी. और जब when we discussed the subspaces of R square and R cube, I told you all the straight lines passing through origin in R square, they are basically what? They are subspaces of R square and R cube. So this is a straight line passing through origin. So it is a vector space and it is also a subspace of R cube. Now anybody else? Izaz Khan, you ask your question. Yes, Izaz?
Sir, I already asked the question.
Okay, lower your hand then. Anybody else who has raised the hand? I don't know. I cannot see here. No. So let's move forward. Now, what is the algebraic multiplicity of lambda here? Lambda is repeating only one time. Means lambda is not repeating here. It is distinct value. So algebraic multiplicity of lambda is 1. And what is the geometric multiplicity of lambda 1? Corresponding to lambda 1, we can find only one vector. So its geometric multiplicity is 1 as well. I hope you understand it now. Now I'm going to erase this, and now we are going to discuss the next slide. This one. Now we consider the case 2, in which we are going to find the eigenvector corresponding to lambda 2 is equal to 2. Now let u1, u2, u3 be an eigenvector corresponding to lambda 2 is equal to 2. We use again this equation, this one, and we assume that lambda I minus a times u is equal to 0, where we insert the value of u from here, we insert the value of lambda, which is lambda 2 is equal to 2, and we insert the value of a. After solving, we get this homogeneous linear system. I hope you can solve this homogeneous linear system by using Gaussian elimination, by reducing it into echelon form, and then we can get basically the solution of this linear system. Now let's move to the slide 21. Now we know that lambda 2 is equal to 2. Then inserting the value of lambda in that homogeneous linear system, and after solving it, we get this set of equations. Now you can see that in this solution we have two independent variables, two free variables. u1 is equal to minus t, u2 is equal to r, and u3 is equal to t. So there are two free variables. Now when we try to write u in this form, u1, u2, u3, u1 is minus t, u2 is r, and u3 is t. Now we need to take these variables common outside this vector in order to find eigenvector. So from the first and third, we take common t. We'll get -1, 0, because here we don't have any t. We get 1 here, plus r. R we can take common only from here. So we get 0, 1, 0. So corresponding to lambda 2 is equal to 2, how many eigenvectors we obtain? 2. So what will be the space generated by these two vectors? This one and this one. This will be a plane in R cube. And that plane will be what? Will be an eigenspace corresponding to lambda 2 is equal to 2. Now, how many vectors or what vectors are generating that eigenspace? We call that eigenspace is E lambda 2. So this is another eigenspace, which will be an infinite space. This eigenspace will be a vector space, and this eigenspace will also be a subspace of R cube. And these two vectors are generating this eigenspace. So the set of these two vectors, this set will be the basis for this eigenspace. Means this set is generating that plane, that eigenspace. Sayyid Ali Akbar, yes, you go ahead, ask your question.
सर ये सेकंड वेक्टर किस तरह जनरेट हो रहा है? आप देखें यहाँ पे आप जो हमारा मैट्रिक्स है उसमें तो r तीनों 0 हैं, तो हाउ कैन r if it is 0 create a space?
कहाँ पे r, बेसिकली r क्या है? r को हमने जब कॉमन लिया तो we get a vector 0, 1, 0. It's not 0. You respond to me, Sayyid Ali Akbar.
सर ये हमने ये दूसरा क्यों लिया? Isn't t enough? t का एक वेक्टर लेना काफी नहीं है?
देखिए आपके पास ये सॉल्यूशन आया ना, आपके पास ये, this is your solution. How many free variables do we have here? 2 free variables. Now when we write u in this term, u1, u2, u3, अब यहाँ पे हमारे पास क्या आया है? We get minus t rt. अब हमने दोनों t को भी कॉमन लिया है, कॉमन लेना है, और r को भी कॉमन लेना है. We split this vector into 2 vectors. कैसे हम इसको लिख सकते हैं? फॉर एग्जाम्पल माइनस टी, 0 एंड टी, दिस वन. इस वेक्टर को हम यूं लिख सकते हैं, प्लस अनदर वेक्टर विच इज 0, r एंड 0. क्या हम लिख सकते हैं इस वेक्टर को इस फॉर्म में? कैन वी गेट अगेन माइनस टी, r and t. This is what we obtain if we split this vector into 2 vectors. From here, can we write this? Sayyid Ali Akbar, are you agree?
जी सर, समझ लग गई है सर, I understand.
Okay. Now you take common t from here and you take r common from here. We need to find the constant vectors, which will be the eigenvectors of the given matrix corresponding to an eigenvalue. So in order to find constant vectors, we split this vector into 2, and then we take common t and r. So we get constant vectors. So these 2 vectors will be the corresponding eigenvectors for the eigenvalue lambda 2 is equal to 2. Now these 2 vectors will generate a space. कैसे generate करेंगे? अगर हम t की वैल्यू और r की वैल्यू, because t and r both belongs to, t and s belongs to r. t और s की वैल्यूज को वेरी करेंगे तो हमारे पास एक प्लेन जनरेट होगा. वो प्लेन क्या होगा? r क्यूब के अंदर होगा और वो ओरिजिन से पास करेगा. ओरिजिन से क्यों पास करेगा? बिकॉज अगर t की वैल्यू और r की वैल्यू दोनों हम 0 ले लें तो हमारे पास क्या आ जाएगा? यहाँ पे we get 0, 0, 0. It means that plane is passing through origin. So that plane, that eigenspace will be a vector space, and that eigenspace will also be a subspace of R cube. और ये जो set of vectors है, this vector is called the basis for that eigenspace E lambda 2. Basis set क्या होता है? जो किसी स्पेस को जनरेट कर रहा होता है. And what is the dimension of the basis? The number of elements in the basis set, is called the dimension of a space, dimension of a vector space. अब इसमें कितने एलिमेंट्स हैं? 2 एलिमेंट्स हैं. तो इस आइगन स्पेस की डायमेंशन क्या होगी? 2 होगी. So dimension is the number of elements in the basis set of a vector space. So that we call the dimension of that vector space. I hope that answers the question. I hope you understand everything. If you have any question, you can ask me. Yes, I need to erase all these things. Then we move to the next slide. I hope you understand everything. Algebraic multiplicity and geometric multiplicity. There are some properties of these two properties, algebraic multiplicity and geometric multiplicity. We need to remember these things. In general, algebraic multiplicity and geometric multiplicity of an eigenvalue can differ. Algebraic multiplicity can be different from the geometric multiplicity. क्योंकि अभी हमने कहा कि अगर एक eigenvalue है, उसके corresponding if we get 2 eigenvectors, तो eigenvalue की algebraic multiplicity 1 होगी और geometric multiplicity 2 होगी. It may differ. So geometric multiplicity can never exceed the algebraic multiplicity. Geometric multiplicity can never exceed the algebraic multiplicity. Yes, someone has any question? Yes, your question is, can we say that dimension of the basis is the number of geometric multiplicity? Yes, you can say. Dimension of the eigenspace, अगर आप more generally इसको कहें, तो dimension of an eigenspace is the geometric multiplicity of the eigenvalue. Now, geometric multiplicity can never exceed algebraic multiplicity. Means, in the previous example, we saw that lambda 2 is equal to what? Lambda 2 is equal to 2 is a repeated root. The algebraic multiplicity of lambda 2 is 2, and the geometric multiplicity of lambda 2 is equal to again 2. It cannot be 3. So geometric multiplicity cannot exceed algebraic multiplicity. So your question is it possible for an eigenvector not to pass from origin? Yes, it is possible if there is no free variable in that eigenvector and all the entries of that eigenvector are non-zero. Then we don't have, then that vector is not passing through origin. Eigenvector, if it is 0, 0, 0, then it is basically origin. We cannot say that eigenvector is passing through origin. We can say that an eigenspace, which is a subspace of a vector space, that should pass through the origin. Why geometric multiplicity can? The question is why geometric multiplicity cannot exceed algebraic. It's a theorem. We have proved it. Here on this slide, I have just written some of the major points which we need to remember. Algebraic multiplicity, again, it is possible that lambda 2, अगर previous example में यहाँ पे lambda 2 की algebraic multiplicity क्या है? 2 है. It is possible that we find only one eigenvector corresponding to lambda 2 is equal to 2. Means algebraic multiplicity lambda 2 की क्या है? 2 है. लेकिन इसकी geometric multiplicity, it could be either 1 or 2, but it cannot be 3. It cannot exceed the algebraic geometry of any eigenvalue. Okay, I hope that answers the question. In the previous case 1, algebraic geometry lambda 1 की क्या थी? 1 थी. इसकी geometric multiplicity क्या है? कितने eigenvectors we have found here? corresponding to lambda 1 is equal to 1, only one vector. We cannot find two vectors here. This is what that property says. The third one is, you can see here, the geometric multiplicity is always less than or equal to algebraic multiplicity. This is what we have discussed. Now, this is the very important case which we are going to use in our further concepts. It is that it is a fact that summing up the algebraic multiplicities of all the eigenvalues of an n cross n matrix A gives exactly n, means order of the matrix A. This is a very important point. I need you to remember this point. We will use this point in our next concepts. Means, for example, in the previous slide, if we sum up, sorry, if we sum up the geometric multiplicities, which are what? In case of lambda 1 is equal to 1, what is geometric multiplicity here? 1. Or in the case 2, sorry, geometric multiplicity of lambda 2 is equal to 2 is what? It is 2. Geometric multiplicity is 2 here. We have seen here. So geometric multiplicity is 2 here. Lambda 2 is 2. So if we take the sum of geometric multiplicities corresponding to all eigenvalues, what do we get here? For this example, we get 3. We get 3. So which is equal to the order of a matrix. The question is in the chat window, is it possible to have an eigenvector without any free variable? I don't think so. I don't think so, because homogeneous linear system which we obtain by inserting the eigenvalue, we must obtain the coefficient matrix. The coefficient matrix in that homogeneous linear system must be singular. क्यों? क्योंकि हमने आइगन वैल्यू को कैसे फाइंड किया है? We put the characteristic equation is what? Determinant of lambda I minus a is equal to 0. जब हमने इसका determinant 0 पुट किया है, we made sure कि जो coefficient matrix है वो singular हो. Otherwise we don't get the non-trivial solutions. I hope that answered the question. Yes, the question is, we can only find all this if system is consistent. We can only find all this non-zero lambdas, non-zero vectors, only if the system is inconsistent, not consistent. Inconsistent means the system has infinite many solutions. In that case, we can find non-zero eigenvalues, we can find non-zero eigenvectors. Because the coefficient matrix is always a singular, so we must have at least one free variable in the solution of that corresponding homogeneous linear system. Agar free variable nahi hoga, so we will get what? We'll get only the zero solution. Because free variable nahi hoga, to ye jo coefficient matrix hai, ye non-singular hoga. Non-singular hoga, then we can take that matrix. If it is non-singular, then we can take this matrix on the other side as its inverse. We multiply it here basically. Sorry, we multiply on the left hand side here. अगर इसका inverse दूसरी side पे multiply करें, तो आपके पास answer क्या आ जाएगा? Zero vector आ जाएगा. And we are not interested in zero eigenvectors. The question is, but the system will be consistent for it to have solution. Yes, sorry, consistent hoga. The system must be consistent with infinite many solutions. It will not be inconsistent, because the inconsistent systems, they do not have solutions. Sorry, I did mistake in the previously. I hope you got my point. If anybody has any question, you can ask me. So this point is very important. You should remember this one. This one is that the algebraic multiplicities of any eigenvalue, okay, and the geometric multiplicities as well. Algebraic multiplicities का sum या geometric multiplicities का sum अगर हम लें तो आपके पास क्या आना चाहिए? Order of the matrix आना चाहिए. ठीक है? And this is particularly important for geometric multiplicities. If the geometric multiplicity, the sum of geometric multiplicities of A is equal to this must be equal to the order of a matrix. Means अगर आपके पास eigenvalues repeat भी हो रही हैं तो उसके corresponding जो eigenvectors हैं वो उनका number जो है that number should be equal to the order of a matrix. So this is very important. We will use this concept or use this fact in further concepts of diagonalization and some other. I have done a mistake here, algebraic. It should not be algebraic. It should be geometric. It's a typo mistake. Geometric. Geometric multiplicity. It is valid for both, but the fact for geometric multiplicities we will use for the further concepts of diagonalization. I hope that answers the question. Now we are going to discuss the next slide. If you people have any question, you can ask me. Now, so let's move forward. Now this is another definition. How do we find eigenvalues and eigenvectors for linear transformations? The definition is if we have any transformation, a linear transformation, it should be operator. Why it should be operator? What is the definition of operator? A linear transformation from a space to itself means these two spaces should be same. If in a linear transformation these two spaces are identical, then we call that linear transformation a linear operator. We know that the definition of linear operator is what? T of x is equal to what? How can we write? If somebody has any question, same dimension. Yes, you can say both the vector spaces or both the spaces should be of the same dimension. Now, how do we define a linear transformation? How to find eigenvector and eigenvalues of a linear operator? We write this equation: T of x is equal to lambda x. This is again same as we find the eigenvalue and eigenvectors of any matrix A, because T of x can be written as AX. We know that T of x can be written as AX. Now AX is further equal to lambda x. This one. For example, we need to find the eigenvalues and eigenvectors of this linear operator T from R cube to R cube, and we are given by definition the linear transformation is defined in this way. So T of x1, x2, x3 is equal to 2x1 minus x2 minus x3, comma x1, x3, and then comma minus x1 plus x2 to x3. Now we need to find the eigenvalues and eigenvectors corresponding to this linear transformation. How do we find it? We just write this given linear transformation in the form of a matrix first. We can write the given transformation in the form of the matrix transformation, because we know that every matrix transformation can be written in the form of a matrix, this one. Now, once we have written the matrix, that linear operator or the linear transformation in this form, T of x is equal to AX, where A is what? This one. Now, it is same as finding the eigenvectors and eigenvalues of this matrix A. The eigenvectors and eigenvalues of this matrix A will be in fact the eigenvalues and eigenvectors of this linear transformation. So it is the same question, and we need to solve. The eigenvalues and eigenvectors of A will be the eigenvalues and eigenvectors of this linear transformation. I hope you understand. If you have any question, you can ask. Now, let's go to the next slide, which is the 25 slide. I have given some of the exercises for you people to do yourself for your practice. We need to find, you have to find the eigenvalues and eigenvectors, and you need to find basis for the eigenspaces for the following matrices. This one, this one, this one, and this one. I hope you can find the eigenvalues and eigenvectors and eigenspaces for these matrices. I also recommend you to find the algebraic multiplicities of the eigenvalues corresponding to these matrices and find the basis for the eigenspace. Similarly, here are some other exercises I need you to do yourself. The question 2 is matrices given in exercise 1 are invertible, and this question number 3, you are given a linear operator. You need to find the eigenvalues of and eigenvectors for this linear transformation, which is defined by reflection about xy plane, orthogonal projection, and so on. Similarly, you have to do this question. Now, for the eigenvectors and eigenvalues, we have discussed everything. If you have any question, go ahead. You can ask. I told you you were. I think you were not listening me. What is the basis of eigenspace? The set of vectors which generate the eigenspace is basically the basis for that eigenspace. And what is the dimension of that eigenspace? You have to do these questions yourself. Try them yourself at home. If you have any question, you can ask me later on in the next lecture. You can discuss the solutions of these questions with me in the next lecture. Going to discuss the diagonalization of a matrix. How to diagonalize a matrix? First, we need to discuss what are the similar matrices. If we are given two matrices A and B, then we call A is similar to B or B is similar to A. If there exists an invertible matrix P such that B can be written in this form, then we say that B is similar to A. I repeat, the definition is, if we are given two matrices A and B here, then we say that B is similar to A if there exists some invertible matrix. This P matrix, we call it invertible matrix. It should be invertible. Its inverse should exist, because here we have P inverse. If P doesn't have inverse, we cannot have P inverse. So the relationship is two matrices A and B are similar if B can be written in this form: P inverse A times P, where P is an invertible matrix. For example, if we are given this A matrix and P matrix, we can find the B matrix which is similar to A. How do we find it? Let me erase this thing. We go to the next slide. What we do here, first we need to find P inverse. I hope you people can find inverse of a matrix if the matrix is given. If P is given, you can find P inverse by using any method we have discussed in the previous lecture, how to find the inverse of a matrix. There are several methods: adjoint method, cofactor method, and what we can reduce the matrix into identity by using row operations. Yes, if you have any question, you can ask me. Umar Sheikh. Yes, if we'll discuss properties of similar matrices later on. You can say that if B is similar to A, then A must be similar to B. And either of these two matrices, if one matrix is similar to other, then the other must be similar to the first one. So that is, if A is similar to B, then B must be similar to A. We'll discuss this later on while discussing the properties of similar matrices. So how to find, for now, we are discussing how to find similar matrix B if A and P are given. If P is given, first we need to find P inverse. I hope you can find P inverse by using the techniques we have discussed earlier. Now, after finding P inverse, we multiply all these matrices. We put P inverse here, we put P inverse here, we put A here, and then P here. Then we multiply these three matrices. Either we multiply first these two and then we multiply with P inverse, or you can first multiply P inverse and A and then multiply with P. We get a single matrix B, which must be similar to A. If anybody has some question, you can ask me a question in the chat. There is a question. We are discussing similarity. What are the advantages of similarity? We'll discuss in the next slides. I hope you understand. For now, you just see what is the definition of similarity when two matrices are similar. That identity, that is basically the definition of the similar matrices. That is not a theorem. We cannot prove it. It is the definition of similar matrices. Someone has defined this. We cannot prove it. So I hope you understand it more in the next on the next slides. How can I raise my hand? Somebody tell Batul how to raise the hand. Yeah, Batul, you can ask your question. You just unmute your mic and you ask your question.
Sir,
and you have
if
to go
we
to participants, and there you have an option: mute and raise hand. I hope.
sir, can you hear me?
Yes.
Sir, so if we multiply P into P inverse, we get identity matrix, and then if we multiply that by A, we should get B, right? So shouldn't the elements of A and B be equal?
No. The similar matrix is a different notion. It's not kind of equivalent matrices. We cannot get equal entries of A and B. Similar matrices is a different concept than equivalent or equal matrices. Okay. Why we are discussing similar matrices? We'll discuss this on the next slide. Why similar matrices are important. So here are some of the properties of similar matrices which we are going to discuss. For example, the first one. No, the question is, can we multiply P with P inverse and then A? No, it is not possible. We cannot change the order of P inverse A and P here in the similar matrices. You cannot write AP is equal to PA because the commutative law in matrices does not hold. AB is not equal to BA. We cannot commute two matrices. Okay, so we have to multiply P inverse A, P in this order. We cannot interchange A and P. So what is the advantage of similar matrices? Why we are discussing similar matrices? Similar matrices have many properties in common. For example, the first one is similar matrices have same determinant. How can we prove it? I have given the proof of the first property only. The remaining property, which we will discuss, I don't give you the proof. You can find proofs in some linear algebra books. We are not here. We don't discuss here the proof of the theorems. This is just for your convenience, for your understanding. We need to prove determinant of A and determinant of B is they are equal. Because the first property of two similar matrices is that their determinants are same. We need to prove this. We consider determinant of B. We can write B in this term, in this way. We put the value of B, P inverse AP. Now, using the property of the determinant, we can take the determinant of this thing, determinant of this thing, and determinant of this thing. Because determinant of A into B is what? Determinant of A into B is equal to what? Determinant of A and into determinant of B. This property we are going to use here. Determinant of A times, sorry, I don't have determinant of, sorry, B. So this property, by using this property, we can write this determinant of whole thing into this determinant of P inverse times determinant of A, determinant of P. Now we know that determinant of P inverse is equal to what? 1 over determinant of P. Now we can cancel out determinant of P with determinant of P. We get what? Determinant of A. It means determinant of B is equal to determinant of A. So this is a very important property of similar matrices. Yes, Heather Iqbal raised the hand. You go ahead, you ask your question. You unmute your mic and then ask your question.
So will all the matrices which have the same determinant be similar?
No. Because similar matrices must satisfy this relationship. Then they will be called similar. Any two matrices which they have equal determinant, they may not be similar matrix. Okay. Any other question? Somebody has raised the hand? No? Okay, we are moving forward. There are other properties which similar matrices have in common. For example, if we have two matrices A and B which are similar, then the following properties hold. Similar matrices have same determinant, which we have proved on the previous slide. Second is, if A is invertible, any matrix A is invertible if and only if B is invertible. What does it mean? If A is invertible, then its similar matrix, which is B, it must be invertible. If B is invertible, then A is invertible. Third property, characteristic polynomial of similar matrices are same. You can try it. If we have two matrices which are similar, then their characteristic polynomials must be same. If their characteristic polynomials are same, then they must have same eigenvalues. They must have same roots. So the fourth one is similar matrices have same eigenvalues. Eigenspace dimension means dimension of the eigenspaces of the similar matrices corresponding to a particular value of eigenvalue that should be same. Means the geometric multiplicity of two similar matrices are same. Next, the sixth property. Similar matrices have same rank. Now, I hope you know what is a rank. Rank is the number of non-zero rows in an echelon form of a matrix. Now, what is the next property is similar matrices have same trace. Now, what is trace? I hope you know. What is the trace of a matrix? Trace of a matrix is the sum of its diagonal entries. That is the trace of a matrix. For example, on the previous slide, if you want to verify this thing, you can take the sum of the diagonal entries of A and sum of the diagonal entries of B. Okay, the sum of diagonal entries of B and sum of diagonal entries of A must be same. This is what the trace of a matrix. Now the eighth property is every square matrix is similar to itself, because we can write A in the form I inverse AI. Somebody has the question. The question is, these properties mostly originate from the fact that the determinants are equal. Yes. No, they are different. The determinant is same, means they can have similar eigenvalues, they can have similar, you can say polynomials, but their rank, their trace, this is a different thing. We need to prove all these properties, and there are proofs for all of these properties. Now the ninth property is, if A is similar to B, then B is similar to A. It is obvious. We can prove it as well. Okay, how can we prove it? We just take P inverse on the other side and P on the other side. Then A will have a similar kind of expression as we have this. Or we can write, I can prove it for you people if you want me to. So let me erase this thing first, and then I can. Now, how can I prove it? I can write A is equal to, I took this P inverse on the other side, and we can write this P, and then again I took P here on the other side. I can write B and then P inverse. Now, according to the definition of similar matrices, P inverse should come first, but here we have P, not the P inverse. Now this further can be written as P inverse whole inverse, this one, times B, and here we have P inverse, this one. Now if we consider P inverse as another matrix, which is Q, then we have Q inverse B and Q here. Okay, now this is what? This is A is equal to Q inverse BQ. So what does it mean? A is similar to B. So we get the same kind of expression as we have in the definition of similar matrices. So the last property is, if B is similar to A, then A must be similar to B. I hope you understand it. If you have any question, you can ask me. Q is another matrix which we call P inverse. Here we have assumed here that Q is what? Q is inverse of P. Q is P inverse. I wanted to write the same notation here as we use for similar matrices. Here in similar matrices, if B is similar to A, then P inverse should be on the left hand of A, left side of A, and P should be on the right hand side of A. This is basically the definition of similar matrices. That's why I have assumed here, because P inverse will again give us P. So it is same as the P. So in order to convert this notation into this, I have written this. I hope that answered the question. If you have any further question, you can ask me. So you can see that similar matrices have many properties which are common. Now, what is the advantage of all this thing? For that, we need to discuss another example. That example 2. I consider another A which is given here, and another P which is given here. We need to find a matrix B which is similar to A. What we do, first we need to find inverse of this matrix B, which I hope you can find easily. I have given here the P inverse. Now what we do in order to find the B, we write B is equal to P inverse AP. We write here P inverse, here A and P. We multiply all these three matrices, we get this thing. Now what is this thing, this matrix B? If we look at this matrix B, we can see that it is a diagonal matrix. It is a diagonal matrix, and this matrix P is similar to A. What if there exists a P so that when we multiply P inverse and P, this expression we get always B as a diagonal matrix? Is this possible? Yes or no? Yes. For any matrix A, we can find a matrix P which transforms the matrix A by solving this expression, which transforms the matrix A into a diagonal matrix. This is possible. Now, the question is how to find such P which transforms the matrix A into a diagonal matrix. This is always possible. Now, if this is not always possible, but there are some conditions I'll tell you later on. Now, for any matrix A, I'm repeating here, for any matrix A, there exists a matrix P. We can find such P which transforms the matrix A into a diagonal matrix, which is a similar matrix to A. If this is possible, then how to find such P? If we can find such P and B is similar to A, where B is always a diagonal matrix, then our computations for A will be very much simplified. Because it is very easy to find determinant of B, and determinant of B must be equal to determinant of A. It is very easy to find eigenvalues of B as compared to A. अगर हम eigenvalues B की find कर लें तो वही eigenvalues A की भी होंगी. If we can find the rank of B, that will be the rank of A. If we can find trace of B, that will be the trace of A. I hope you understand this. So note that B is diagonal matrix. Using properties of similar matrices, everything, e.g. determinant, eigenvalues, rank, and all the properties of A and B, they have same. Then by using B, we can find everything for A very easily. I hope you got my point. If you have any question, you can raise your hand. You don't have any question? Should we go? Should we move forward? Okay. So what is the purpose of sorry, what is the purpose of finding similar matrices? Because they have a lot of properties in common. And if we can find a particular kind of P which transforms the matrix A into a diagonal matrix, then our calculations will be much simplified. Somebody has raised the question. What will be the values, eigenvalues of B? No, B, if B is a diagonal matrix, its diagonal entries will be its eigenvalues. If we solve that characteristic equation, you would see that 2, 2, 1 will be the eigenvalues of this matrix A. And we can find the corresponding eigenvectors. Eigenvectors will exist because when you write that equation, in order to find the eigenvectors, we write, sorry, not this one, we write an equation which is what? Lambda I minus A or B times x is equal to 0. When we use this equation, lambda I minus b, we solve this, you would see there are eigenvectors corresponding to each eigenvalue lambda 2, 2, and 1. Somebody has asked the question. You just raise your hand. Mohammad Faizan, you just raise your hand and ask your question. They will pass through the origin. The eigenvectors of the question is eigenvectors of B won't pass from the origin. This is the question. They will pass. I hope you won't have noted here. I have taken here in this example the same matrix A which I have taken in the example 3. The matrix in the example 3 on the previous slides of eigenvectors. We have found the eigenvalues and eigenvectors of the matrix A. Okay, let me erase this thing and then we'll discuss this one. Now, this is the same matrix which we have already calculated the eigenvalues and eigenvectors on the previous slides. We have found the eigenvectors and eigenvalues of this matrix, and we obtained what? Lambda 1 is equal to 1 and lambda 2 is equal to 2, 2. That was the repeating eigenvalue. Go back to the previous slides and check the eigenvalues of this A matrix. And corresponding to eigenvalues, these eigenvalues, we have also found the eigenvectors. We have found that there is one eigenvector corresponding to 1 and two eigenvectors corresponding to lambda is equal to 2. So there exist eigenvalues and eigenvectors for this matrix B as well. Because the eigenvectors and eigenvalues for these two similar matrices, they must be same. तो B की eigenvalues वही होंगी जो A की होंगी. B के eigenvectors वही होंगे जो A के होंगे. We have already discussed it. ठीक है? I hope you got this point and you understand it. Next, we are going forward. Now, the question is how to find such P. How to find such P, which transforms the matrix A into a diagonal matrix. For that, in order to discuss how to find P, first we need to find the diagonal. We need to discuss diagonalization of the matrix A for a given matrix, for any matrix. First, we discuss how to diagonalize a matrix A, and then I'll tell you how to find that P. In fact, during this discussion, we will find that how to write that P or how to find that matrix P. Now, what is the diagonalization of a matrix? If a square matrix A is said to be diagonalizable if it is similar to some diagonal matrix, say B. Now, on the previous slides here, this matrix A is diagonalizable. Why? Because there exists a matrix P which transforms it into a diagonal matrix. Then B is similar to A. Now here, this B is similar to that A, and B is a diagonal matrix. What do we say that this P matrix diagonalizes A? This is what diagonalization is. Okay, a square matrix A is said to be diagonalizable if it is similar to the some diagonal matrix B. If A is similar to B, then there must exist an invertible matrix P such that P inverse AP is equal to B, and where B is the diagonal matrix. In this case, we say that P is said to diagonalize A. Now there are two questions: when a matrix is diagonalizable and how to find that diagonal matrix B. Someone is asking the question. You go ahead. It's time. Let me finish in 2-3 minutes. Yes, 2-3 minutes, and we'll finish this lecture. Now, a square matrix A is said to be diagonalizable if there exists some matrix P which transforms that matrix A into a diagonal matrix, and B, where B is similar to A. when a matrix is diagonalizable, there is a theorem. I don't want to discuss this theorem right now. We'll discuss this theorem in the next lecture. For the today's lecture, we stop here. If you have any question, you can ask me related to today's lecture. If you have any question, go ahead, you can ask. If you don't have any question, I'm going to terminate this meeting. Thank you very much for your participation in this online lecture. Hope to see in the next lecture on coming Monday. Thank you very much, and stay safe, and अपना ख्याल रखें, अपने इर्द गिर्द लोगों का ख्याल रखें. Thank you very much. Allah Hafiz. There are questions in chat. Pause share. Let me